Geology is the study of the whole Earth, all the landforms, the mountains, the rivers, the seas, and all the different kinds of stones that are in the Earth. And today, because we're studying the geologic column, which is sort of a historical study, I want to begin by making sure that you just understand three basic rock forms. The first one is what is a shale. And a shale is a kind of a stone that's formed with a lot of organic matter. A common way to form a shale is to have a lake that's around for a very long time, and the little fishes or other creatures swim through the lake, and they drop their little droppings behind them down to the bottom of the lake, and then the lake bottom is black and gooey, and time passes and time passes and time passes, and the bottom of the lake gets completely filled up with goo, and then other things happen. The lake dries up and things grow on top and history goes by, and the whole thing gets compressed eventually into a stone, and that stone is going to be a dark stone, a shale, a slate, or coal. But anyway, all of those dark things are shales. The second important kind of stone that's commonplace is what you get. Do you know what you get when you have shells of creatures? Shells of seashells? When the seashells are piled and piled and piled and piled on top of each other, and then they're compressed, then you get limestone. And if you compress the limestone even further by sitting on top of it with, say, a mile of sandstone or something, so you get it really squashed, then you get, does anybody know? Then you get marble. Marble is compressed limestone. And actually, it sometimes is compressed in such an orderly way that the little creatures that made the original limestone are still visible in the marble. If you walk around churches, you'll sometimes see a little curlicue in the marble. And that curlicue is a crinoid. And it's from not thousands of years ago, but millions upon millions of years ago. The scale of time in geology is completely different from what you're used to in human life. Jesus is 2,000 years ago. The pyramids are 3 or 4 or 5,000 years ago. We're talking about the origin of man is maybe 100 or a few 100,000 years ago. Some people say 1 million, I'm not sure about that. But regardless, when we're talking about geology, we're mostly talking, especially historical geology, we're talking about millions of years. And now, here's a question we can ask ourselves. Suppose that I took a drill, a core drill, and just drilled down the ground right around you, all the way down to the magma. What would we find? And the answer is, because we're in eastern South Dakota, do you know what we would find about 100 feet down?
Dinosaurs.
Good answer. But in eastern South Dakota, the interesting thing is no dinosaurs. Western South Dakota. But in eastern South Dakota, by the time you get 100 feet down, and especially right here, who's seen quarries around the city? And what's in the quarries? What are they digging out? Coal? Quartz. They're digging out pink quartzite. And that pink quartzite, all of it, is 500 million years old. That quartzite, the sand, which was compressed together into that quartzite, 500 million years ago, it was sand just being laid down, layer by layer. And what you have on top is just the stuff from the glacier. The glacier came from up north, Canada, wherever, and it dropped some stones behind, but it pushed ahead of us everything else that was there on the surface. So if you go to western South Dakota, yes, you get the dinosaurs and you get the coal and you get all kinds of stuff. But in eastern South Dakota, the glacier just shoved that all off. And the only thing that's left is the stones that were sort of caught in the bottom of the glacier. And when the whole thing melted, those stones were left. And then oils and sands and junk that just, floats in. So we have 100 feet of what's called glacial till. And then all of a sudden, it's stuff that's 500 million years old. Normally, when we speak of the geologic column, we're speaking exactly of those 500 million years. because something very special happened about 543 million years ago. How could we be so exact? Oh my goodness. Here's what happened. There were other creatures. There were many kinds of creatures. But they didn't have shells. They didn't have bones. They didn't have much in the way of teeth. And they didn't leave much in the way of fossils. For a very long time, all the way through my childhood and part of my adulthood, the thinking was the whole group of animals all just turned up in the Cambrian 540 million years ago. How did that happen? But now we know the animals were there, but they didn't have shells. And what seems to have happened is that all of a sudden the ocean water, which was kind of milky, clarified. And when it clarified, then it mattered whether whether animals had eyes. And the ones who had the best eyes ate the others. Unless the others had armor on, then they survived. So who had the biggest teeth? Who had the strongest armor? That's what decided who survived. And very quickly, any animal that had a little bit of armor, those of its offspring that had the most armor survived the longest, and that's how evolution works. So anyway, as we go around the world digging these posts underneath different people, we have an idea of all of the kinds of rocks that used to be in that part of the world. And what we're going to do now is we're going to go up to North Dakota to a place called the Williston Basin. And in the Williston Basin, because they were drilling for oil, they actually drilled down, took these cores out and examined them, and looked at each core. And somebody named Glenn Morton posted a record online of exactly what kinds of things were in these cores. And it's a fascinating story that it makes. So we're going to go through that. We begin, you have your papers there in front of you. We begin at the top of the Williston Basin. And all that's there in the top, you see a little plant there growing at the top, because that's what happens at the top. And underneath, you have the kinds of what's called glacial till, just different kinds of rocks all mixed together, because a glacier, it's just a big, huge, enormous piece of ice. And as it's going along, if a stone gets stuck in the bottom of it, it just stays there and gets moved along. So glacial till. And underneath the glacial till, then we begin to have a mixture of sands and shales. The dark part in your images is the shale, and the lighter part is the sand. Sand is interesting. Shale is likely to be the bottom of a lake. And what's limestone likely to be? The bottom of a sea. The limestone is going to be the bottom of a sea because it's going to be where the shells have fallen down. Sandstone, what is sandstone the bottom of? Why would sand be anywhere? Where does sand come from? But here's what happens. Somewhere near the beach, upriver, there's a mountain. And the mountain is maybe getting hot and cold, or maybe getting cold and freezing, and it's crumbling to bits. And the little streams are carrying the sand down the river to the lake or to the sea. And so sandstone always means once there was a mountain. And if there's a huge amount of sandstone, there might not even be a mountain left. But still, you can drill down into the sand and see how deep it is and say, wow, that must have been a mountain. That must have been a huge mountain. That must have been a range of mountains. So there are some mountains that all we know about them is that they left us a huge, enormous amount of sand. So anyway, there are these sands, there are fossils, and there are bits of shale. And when we go farther down, we finally come to a place where there's clay. The interesting thing about clay is this. Clay is very fine. Sand that you have on a beach is mostly quartz. And the reason for that is that quartz is a very hard stone. Did you ever talk about Mohs hardness scale? Anyway, you've heard that a diamond is very hard, and you know that chalk is very soft, and in between there are other things. Quartz is, I think, 9 on a scale of 1 to 10, where the diamonds are 10. And feldspar, you can pass this around so you get an idea of it. When you have it, turn it, and you'll find that there's one place where all of a sudden it shines because you're actually seeing the crystal surface. Feldspar is like quartz except that it also has aluminum in it. And it erodes much more easily. And when you have a beach that's made of feldspar, the sand is very soft, but also the sand breaks up and it doesn't last as long. And if it breaks up completely, then you end up with a clay. And that's what's in this formation under the Williston Basin. And down below the clay, then you come to each of these formations that you find in the Williston. We call it a basin. It just means that's just what it was called in Williston. We're actually drilling with an oil company. So we're going to drill down, get a core, and say, what's this? What's this? This is clay. And the next thing that we come down to is we start to find sand, but we also start to find pieces of fossils. And it's very interesting because the different fossils really identify what kind of a world was there. We do actually have some fossils here of little sea creatures. We have fossils of bits of trees, plants, animals, and we have fossils of little creatures that burrowed into the shale when it was soft mud and made their home in it. Towards the bottom of that, page 125, you see some little starry things. And what those stars represent is a specific moment in history. 65 million years ago, all over the earth, wherever you drill for oil, wherever you drill for anything, when you get down to this level, there's a certain level, what you find is that in the soil there is an element called iridium. Iridium is just one of the elements on the periodic table, but it's not common on Earth. It's not common in any of the soils. It's common when you have something from outer space. And so when we have iridium all over the Earth, at this level, everywhere, what does that mean? Meteorites. It means that something came here from outer space in such a cloud that it completely, I won't say blanketed the earth, it was probably, just sprinkled. But the point is, the whole earth was blanketed. And here's what's even more interesting. Turn the next page and you see a dinosaur fossil. There are no dinosaur fossils above the iridium layer. All the dinosaurs are below. Very few exceptions come because it looks as if some old soil had gotten pushed up and crumbled down, and so then there were dinosaur fossils out of place. But in place, the dinosaur fossils are all below there. And that's actually giving you a history. It's saying this is when the dinosaurs all died out. And that is 65 million years ago. So wherever you find the iridium anomaly, meaning unusual thing, that's the marker. 65 million years and below are the dinosaurs. So you see the dinosaur fossils, you see some sands, you see some places where you have a shale, and then in the shale there's a cut. Now what would that mean? Why would there be a cut in the shale? Because remember, the shale is being laid down year by year by year. And so a cut, kind of an odd deal. Here's what's happening. You have a shale bed of some kind. Maybe it's not really that hard yet. Maybe it is pretty hard. And a stream begins to flow through it and across it. And it begins to wear it down. And then you begin to have a big crack in the shale where the water and the ice are breaking it down. And then, time passes, the stream dries up, and it gets all full of sand. So then you have this layer of shale with a bit of sand in it. So that's what's represented there, is that there are stream beds cut into the shale. And then there's ferns and things like that. And there are sometimes coal beds. Coal is kind of interesting. Coal means that you had a huge flood that killed off all the vegetation, and it all fell and died down, got squashed down. Other things came on top of it. And then you have a layer of shale, but there's no mud in it, there's no sand in it, there's no other stuff. It's just all organic matter, all black. And in that coal, there are usually tons of fossils. And the interesting thing is, each level of, there's a coal seam, and there's all kinds of other stuff, and then there's another coal seam, and then there's other kinds of soils, the sea creatures and stuff, and then another layer. And in each layer of coal, there are different fossils. The lower layers have no bugs at all. Then the upper layers, you start to have bugs, and you're going, oh, so there weren't any bugs in those ancient times. So the coal really tells us a lot. The other thing that you see here in the greenish color is a layer of bentonite. Bentonite comes from volcanic ash. The layer of volcanic ash is 100 feet thick. Okay, do you have any concept what it would mean to have a volcano lay down 100 feet of dust? I mean, you wouldn't be here telling me about it. We only talk about these things when they happen some other time, some other place. And 100 feet is deep enough that wherever it happened, which at the moment is North Dakota, it happened everywhere. It has to have blanketed North America. It has to have been very hard on life. And below that we have some more, we just have some alternating limestones, and then these other kinds of volcano soils, and back and forth. And wherever I've drawn something that looks like a little bit like a brick wall, except it's white, that represents more limestone. And you can see that there are places where the limestones and the shales go back and forth. If you turn on to page 133, you can see the fossil that we originally passed out, the ammonite. So ammonites are very interesting because there were ammonites all the way through what's called the Mesozoic, the period from that 65 million years ago when we had the iridium anomaly, all the way up to 250 million years ago when all of the trilobites died out. All the way through the Mesozoic, what we have is we have ammonites, and they change over the millions of years. I mean, we're talking about 70 or 90 million years, I can't remember what, long period of time. And the ammonites keep on changing that whole time. Actually, changes. You have a curlicue like this, and then you have a curlicue that's like this, and then you have a curlicue that's like this, and they just get more and more frilly as time goes on. But the result is that when you have an ammonite fossil, you actually know where you are in the Mesozoic. You know how far back you are in the Mesozoic. It's what's called an index fossil that really tells you where you are. And that's kind of fun because really it's hard when you have so much time. We're talking about millions of years and we're going all over the world to have something that will actually place you in time. Now, I want you to turn to the next page where it says the Triassic, the Spearfish Formation. And the striking thing is if you look at the Spearfish Formation and then the Paleozoic, what's the first thing that strikes you when you look at these pages compared to all the others? Actually, it's striking you so hard you're not even seeing it. They're pink. They are so pink. Why are they so pink? Are you serious? Did you just run out of black crayon? And the answer is no. There seems to have been an incredibly dry period several times during the Mesozoic. Of course, the ammonites were living in the water, so they weren't dry, but the land was dry. And when all of the land is dry like that, then all of the iron that's in the land rusts, and all of the sandstones are pink. All of the limestones even are pink because the rusty water comes down from the rivers and goes into the streams and into the lakes and into the sea right nearby. And everything turns red. So you have red limestones. You even have red shales. How many of you have driven to western South Dakota and then started off into Wyoming? And you've seen those incredible red beds. You know what I'm talking about? So Spearfish Formation, guess what that means? We're talking about those things that you're seeing in spearfish. This is what that's about.
Is that kind of like different colored marbles? That's how you get different colored marbles? And
different color marbles can also come from these different, whatever minerals fed to it. Mm-hmm. And what state they were in, because you can have iron that's greenish, but when it's oxidized, then you get these red colors. So in the Spearfish Formation, you have all of these. You have red shales, you have red limestones, and you have, I think you even have red sandstones, red clays. And finally, okay, and one of the things that you have on the first of the red things, before the spearfish formation, is you have a layer of salt. Now, I want to talk a little bit about what it means to have a layer of salt. How can you have a layer of salt? Not just a sprinkling, but an actual layer, like here's some salt, dig it up with a shovel, here's some more, here's some more.
Wait a minute, so that whole white layer is salt?
Yes, I think that whole white layer is salt. The only way you can get this amount of salt is to have, okay, remember, we're in North Dakota. Of course, you know, we're going back millions and millions of years. And we come back to a place where you have mountains on either side of North Dakota. And the sea comes flooding in, and you have an inland sea. We call it a sea because it's salty. And it's connected to the world ocean, but then something happens. I mean, what happens? Earthquakes, whatever. And all of a sudden, it's cut off from the world ocean. It's not being fed by the world ocean, and it's not being fed by enough rivers to keep it. So it completely dries out. And then, you know, life goes on, and this little whatever it was breaks down, and the sea comes flooding in again. And that's the way it is for a while, and then all of a sudden something happens again, and it's sequestered again. And if that happens repeatedly and completely dries down, then you can have a deposit of salt. And that's how we have deposits of salt all over the world. Those deposits of salt mean there was a sea here, not a lake. A lake is fresh water coming down from rivers. A sea means the ocean came in and sat there for a while. And then somehow it siphoned off. And sometimes it just flows off, you know, there's an uplift and it just flows away. But other times it's sequestered, it's held off, something happens, and it's all by itself, and it totally dries down. The amount of salt in this particular deposit is 1/14 of the salt that you would get from the world ocean right now. I mean, it's just an unthinkable amount of salt, just unthinkable. But it's important for a particular reason. I'm just going to take a minute to talk about why Glenn Morton wrote this whole paper and why he posted it. A lot of people have the impression, or are teaching each other, that all of the sediments in the world are the result of Noah's flood. And what Glenn Morton wanted to say was, not really. You can't get a layer of salt 150 or 300 feet deep during a flood. You don't deposit salt during a flood. You can deposit lots of stuff, but not a whole big layer of salt. The only way to get that kind of layer of salt is to have the sea come in and dry out several times to get that amount of salt. So it's not from Noah's flood. And actually, the shales, many of them that are completely black, they're not from Noah's flood either, because the shale requires kind of a quiet time. A lake bottom is kind of a quiet place, but if you have a flood, all different kinds of things are swirling around. The sands come down, the dirt comes down, the shells come in from the sea if you've got a really worldwide flood. So all different kinds of things are mixed together. You're not going to get a nice, clean coal out of that situation. You're not going to get a nice, clean limestone. Some of these limestones are completely pure. Even when you think about the way that marbles look, some marbles are just pure white, and others have these beautiful swirls. You can't get that kind of thing out of a flood, because all the stuff from the shales and all the stuff from the structures would be mixed in together. It wouldn't be layered neatly. To layer it, you need to have a history, okay? So you have this huge salt deposit, and then on the next page we can look at another red limestone. And then you can look at the bottom of that page where that little thing is that looks like a tree that was drawn by Dr. Seuss or something. That's the plant that you commonly see in the church when you have marble with a little curlicue in it. Those little curlicues are crinoids. And they're from that kind of a plant. It's just interesting to see that that picture is there all over the world for everybody to look at. So then on the next page we have some more very dark shales. And then we have something, a funny little thing that looks sort of like a beehive, where it says beside the Duperow formation, there's something called a stromatolite. Stromatolites are being formed now off the coast of Australia, but they're a very unusual thing. They're not formed just everywhere. A stromatolite means that you have an algae growing, and the algae sort of catches dirt, and the dirt gradually pulls in calcium minerals from a water that's very, very thick with calcium. So you can't do this out in the middle of the ocean. What you have to do is you have to have sort of a lagoon that's sequestered off so that you can get so you can get a lot of minerals in the water. So the stromatolites add more minerals each day as the tide comes in, and they become larger and larger very slowly, and you can actually count the layers on them, so it's very interesting. So we have some stromatolites forming now, but these were from long ago, and you know, when they were first discovered, it wasn't clear that there were stromatolites now. You don't see them just everywhere. They require a special environment. Then when you go down below the stromatolites and the prairie evaporates, you come to the Winnipegosis Formation, and what you have is a mixture of anhydrites. Now, salt is one kind of dry mineral, but there's also gypsum. So there's a couple of different minerals that can dry out. And there's also, at the top of the page that talks about the Silurian, there's something called a conglomerate. I know that this looks as if I just pulled it out of my sidewalk when they were changing, but that's not what it is. It is a conglomerate, and a conglomerate is a kind of stone formation where you have a bunch of pebbles or maybe a bunch of shells, and they're all just sitting there together, and somehow maybe they're in a water that has a lot of calcium in it, so it lays down calcium just the way it does. You know how you get sometimes a calcium line beside your sink or in your bathtub? That kind of calcium line, that kind of calcium deposit, can glue a bunch of stones together, or it can glue a bunch of shells together without breaking them down. Normally, when you talk about marble or when you talk about limestone, the shells are broken. Sometimes they're broken down so you can't see any of the old shell. Sometimes they're just piled on top of each other and you can see some of the shell. But sometimes you'll have a situation where the shells and stones are completely intact. They're just glued together. And it just looks as if somebody poured cement on them. So that's a possibility. And then below that, we come to the Silurian. The Silurian is just the name of a period of time. The interesting thing about the Silurian is, again, we're talking about a history. And in this period of time, we have a bunch of limestone. And in the limestone, we also have corals. All the corals of the Silurian are four-sided figures. All the modern corals have 6 or 8 sides. So it's quite specific, and it's quite different, and it belongs to a different period in history, millions upon millions of years ago. A coral is originally a living creature, and so the skeletons of the corals is what we have left. But these corals are different. Then you come to the Bighorn dolomite, and the interesting thing about the Bighorn dolomite, again, you can see that there's an ammonite in there. But I want to say a little bit about dolomite. Limestone is calcium carbonate, CaCO3. Dolomite, calcium magnesium carbonate. Your bones are calcium and magnesium. The shell of a shellfish is a calcium carbonate. And so it's very different. It's a different mineral, and it doesn't wear off quite as easily. There are places where you have a dolomite and then a calcium carbonate on top of it, and the calcium carbonate will wear away and get caves in it, and the dolomite will just sit there. There's actually a famous formation underneath Jerusalem that has to do with this. When David got into Jerusalem by the under passages, The reason why it was possible is that the wells were cut into the calcium carbonate, but the calcium magnesium carbonate underneath was stable, and so you didn't quite realize it was there unless you knew. And boys know what's under, right? You know about the caves on your own property. So anyway, so it's interesting to know what dolomite is. And then we come to the next to last page. I just want to show you something really interesting. There's a Winnipeg formation. Then there's a dark shale. And underneath there's a deadwood formation. And there was a mystery here when they found these two, because here's why. Every sand grain in the world, unbelievable as it may sound, carries the signature of the mountain that it came from. Even if the mountain is gone, we still know this sand grain and this sand grain came from the same mountain. Unbelievable. Well, here we are. We have these two formations, and they have exactly the same sand grains, but there's this whole piece of history in between. How could they be so exactly the same? And people puzzled about this for a long time, and then finally they figured out kind of an interesting answer. Of course, I haven't even talked about the fact that, all these things get laid down flat. The bottom of a lake is flat. When the sand comes down to the beach, the beach may slope a little bit, but basically flat. Everything's flat. So how do you ever get, something that's tipped up? And the answer is, well, you lay it all down flat like this, and then a volcano comes up here. And when it comes up, it pulls everything up, and it just lifts the whole landform up like that. It can lift it up completely on, and it can lift it up and turn it over on itself like that. Not very often, but it does. But what seems to have happened here is that somehow there was, of course, the older thing is first. There was a sandstone, and then there was, a change of weather and stuff, and millions of years passed, and then there was a whole period of time when a shale was laid down, and then something happened far away from the Williston Basin. Who knows how far away? Maybe towards the Rocky Mountains, maybe up the other direction. But there must have been an episode that made things come up, and then this sandstone here broke off here and crumbled down and was relayed. So you have the sandstone down here, and then you have the same sandstone up on top, eroded into it. So, there are these mysteries that the geologists have to figure out. How could these things both be so much the same? Okay. So, and in the end, the last picture is a picture of the trilobite, because the trilobite is such an old creature. You've heard of getting oil from shale, okay? All of the organic matter is where all of the oil comes from. And if you look at this here, which is a quilted version of what you have on your papers, all of these dark sections are shale. 46% of the geologic column worldwide is shale. Yeah, really. And then there's some sandstone. It all comes from mountains. And there's a lot of limestone. But that's really what we're looking at, and that's where the oil is from. Of course, it's hard, it's hard when you dig deeper, and not all shale has lots of oil, because the oil might have been squeezed out and pushed over to somewhere else, some other part of the shale bed. There's just a lot of stuff that happens under there, but shale is where the oil is, and because it is where the oil is, because it is a little bit oily, it's not where the water is. If you dig a well, what you're doing is you're digging down into sandstone. Because if you have a piece of sandstone, you can pour a half cup of water on it and it'll just sit there. In fact, it'll drip out of the bottom of the sandstone. But if what's underneath the sandstone is shale, then that will hold the water. And so you can drill a well into the sandstone. That's the way it works. So the water is in the sandstone, the oil is in the shale, So what you're saying is the oil might sometimes flow into the sandstone, same as the water does.
Yes.
Okay. The reason that things turned red, the iron was oxidized and you had to have a period of dryness. We think also that there was a higher level of oxygen during a certain period of the Mesozoic. And there are several reasons for thinking so. One of them is that there are these dragonflies that are huge, and dragonflies only get oxygen by diffusing through the thorax. They don't have a system where they can breathe it in and get some more. Well, you know, when you start getting this big, how are you going to get enough oxygen to fly just by waiting for it to sort of filter through, you know? And the answer is, we think that there was a higher level of oxygen, maybe as high as 35%. Right now we have 21% oxygen. But there's a little bit of a vulnerability. What happens if you take a room and double the amount of oxygen? So suppose that you wanted to start your wood stove, Linda, and the oxygen in the room were 35% instead of 21%. What would be the effect of starting on the poof? It would start up so fast. Get out of the way. Make sure you don't have a newspaper in front of your face, because this is dangerous. And it appears that there is also a carbon layer associated with the iridium layer. It looks as if whatever came in from outer space had started a bunch of fires and they had just burned out of control. Why? Because at 35% oxygen, you're just not going to have much control over a fire. Bad business. So.
What is that layer called?
The layer where the iridium is called the iridium anomaly often. And it's also called the KT boundary. KT boundary is just to make sure that you won't be able to remember it, because the K is for Cretaceous, which begins with C in English, but it begins with K in German. And Tertiary is the third era, Paleozoic, Mesozoic, and then the third one, the Tertiary. So, and the Cretaceous is the end of the Mesozoic. And it's interesting, here's why it's called Cretaceous. Cretaceous really means chalky. And have you heard of the White Cliffs of Dover? Have you seen pictures of that? Well, the White Cliffs of Dover are chalk, and they belong to the Cretaceous period. And apparently what happened is that the mid-Atlantic ridge was built up at some point towards the beginning of the Cretaceous, or during the Cretaceous. And as it was built up, it raised the level of the world ocean, because then you had a mountain under the ocean, a huge ridge of mountains under the ocean. So you can see that would raise the level of the ocean. And raising the level of the ocean meant that, you know, you have continents, and they're higher in the middle than in the edge, because that's just life, you know, that's how continents are made. But if you raise the water level 100 feet, then a huge amount of the continent becomes a shallow sea. And shallow seas are what you need for making chalks, because chalks are often made of little tiny sea creatures, either or coccoliths, but little tiny creatures that stack up on top of each other. You need to have shallow water. It's not a deep water phenomenon. And there are chalks all over the world during the Cretaceous. They're not everywhere all the time, but there's no other period when you have these huge deposits of chalk. So the huge deposit of chalk, like the White Cliffs of Dover, is a signature of the Cretaceous period, and it's a signature that's worldwide. So some of these things are worldwide. The red beds are worldwide. The chalk beds are worldwide. The iridium anomaly is worldwide. The little things that you see, like, you know, this dinosaur and this, you know, those things can be particular and local. We have soils, representative soils from each of the geologic periods of history, from the Paleozoic, which is Cambrian, Ordovician, Silurian, Carboniferous, Permian, I think I skipped one, and then the Mesozoic, which is Triassic, Jurassic with the dinosaurs, and Cretaceous with the chalks, and then the Tertiary, which is the last 65 million years, and it's broken up into all different kinds. But there are 26 places where you can see representative rock types from each of those periods. Of course, if you have something like a volcano, you know, a great big thing comes up and it pushes everything aside. Or if you have something like a glacier, it'll push everything off. So that in eastern South Dakota, we don't have any of this stuff. It's none of it's there. In western South Dakota, we have something really fascinating. Harney Peak is actually a batholith. A batholith means that something came up that could have been a volcano, but it wasn't. It just, this plume of magma came up, and it didn't really reach the surface. But it pushed everything. It pushed through everything. And then since then, a lot of stuff has eroded off. And the result is that if you walk outwards from Harney Peak, which now is above ground, if you walk outwards, you walk through time from the lowest strata, which would have been right next to it at the beginning, farther and farther and farther up. So all of the geologic eras are represented in western South Dakota, and most of them are at the surface, somewhere within 20 or 50 miles of Harney Peak. It's just quite amazing, completely different. So, and if you go to the Grand Canyon in Colorado, I can't remember, I'm sorry, which parts of the geologic column are missing, but the point is that you had this plain, all this stuff was laid down, and then the whole thing eroded. So there's whole geologic eras missing, and then it quit eroding. And then the Colorado River was flowing across the top, and it continued to uplift. The river didn't cut into the ground. The ground uplifted around the river slowly enough that the river could cut down into it and maintain its... Oh my goodness, how amazing is that? But so when you go and just stand at the Colorado River, you can actually see what I've tried to draw here. You can actually see it across from you, except that some parts are missing. This here is 3 miles deep. 3 miles deep. This here represents 3 miles of different kinds of rocks and soils. So picture yourself walking through those 3 miles and understand how much history there is. We're talking about times when we had a lake, times when we had a sea, times when we had drying out, times when we had sand pouring in from some mountain eroding somewhere. All of these different events taking place sequentially in that one area. And when you start asking yourself, how long is it going to take to build up 300, 500, 700 feet of soil just from fish droppings? Like, okay. You can't do that in any short amount of time. How long is it going to take if we do it just from the broken shells of animals that have died? Long time. How long is it going to take to completely dry out 1/14 of the world's oceans and lay them on top of each other? Lay that salt on top. So it's important to understand this. Glenn Morton really wanted to say, because the love of Jesus doesn't really depend on how old you think the earth is. Who cares what that is? What it depends on is the love itself. And when we look at the beginning of Genesis, talking about 6 days, he's kind of saying God made everything that you see out the earth, and we worship him on the 6th day. So when you look out, you see the sky and the land. And then you begin to look at what the sky is filled with, the birds, and what the land is filled with, the vegetation. So it's really just a description of everything. In the beginning, God made the heavens and the earth. And he did this, and we are going to worship on the 6th day, which is the day of his rest and of his covenant. The rest is the covenant. So every 6th day we say, thank you for the whole of creation. The day thing is just not a good idea to try to squeeze into some kind of a time frame. Even when, creationists will try to say, well, maybe a day is 1,000 years. No, because remember that in Scripture, when we talk about those days, we have all of the flowering plants on day 4, and all of the animals on days 5 and 6. But there are flowering plants that absolutely depend on beetles or on bees for their pollination. They co-evolved. You can't have them 1,000 years ahead of each other, or even one. So it's important not to lock yourself into a position where you're embarrassed, or where you suddenly feel like, oh, wait a second, I was told it was 6 days. Christianity must be a whole pile of foolish ideas. And the crust, which is it's 5 or 6 miles, maybe 12 miles in some places. The crust is not thick. And underneath you have this soft magma. And the magma is circulating just the way, really the way I think of it is how oatmeal looks when you're cooking it, and you can see the bubble, how the boiling goes round and round and the half-cooked oatmeal goes in and out. So it comes and, but whereas on the stove you have one flat pan, on the earth you have your heat source is round. The earth's hot on the inside. Apparently it's hot largely from radioactivity. So that radioactivity is 25% of our heat, even now, is coming from the inside of the earth, not from the sun. So that heat is there. But that boiling means that every now and then you're going to have something boiling up this way and boiling up that way, and that's going to pull on the crust that's up above it. Do you see? Does that make sense to you? And so where it pulls apart like that is where you're going to have mountain building, where you're going to have a volcano of some kind. That's one way of having mountain building. But it's also one way that you have hot springs. If you look in Nevada, that's a spreading regime. But once you have a mountain, what's interesting is that the mountain comes up and all of the minerals react with the air. Or even they react with the air, and once they react with the air, they're lighter than the minerals that have never reacted with the air. And it's also true that where the ocean crust subducts underneath a continental crust, it goes down and it comes up in the middle of the ocean, comes up from the mantle, and as the mantle is pushed over towards a continent, this crustal piece here is reacting with the water. And by the time it gets over here, all of the minerals that came up from the magma have reacted so much that they're quite different. And when they dive down underneath the continental crust, melt, and come back up in some kind of a mountain episode, they are never again as heavy as they were when they first came fresh out of the mantle. So continental crust is lighter than ocean crust. That's the sum of that. So wherever a continental piece of crust meets an ocean piece of crust, the ocean goes down. Wherever continent meets continent, they bump into each other and they can both push up. But the ocean and continent, the ocean goes down and it comes back up and it's continental crust and it's never ocean crust again. So you get more land, but it isn't really more, for one thing, 5 miles out of 8,000 is pathetic, but and we get a small amount of dust from outer space, but basically we don't change. And in fact, the real answer to your question is, you say, how could there be these 3 miles of sediments everywhere? And the answer is 26 places is a tiny number. Many people have said, oh, there's no such thing as a geologic column. It's just different everywhere. It's just different everywhere. Why do you even make this kind of stuff up? And the answer is, particular things are in each different place. As I said, here in eastern South Dakota, there's nothing. This whole geologic column is missing except for just the tippy top. All we've got is glacial till and quartzite. And this whole thing is missing. But in western South Dakota, the whole thing is there, and most of it is sitting on the surface. In North Dakota, we actually have it in sequence. But what we have is the first person to really work this out was named William Smith. He lived in England. And he lived in England at the time that they were mining for coal and also building canals. And he was involved in a very practical way. He wasn't an upper class kind of a guy. But he noticed that there were particular kinds of fossils in particular coals, and he began to see in his mind that if you had a mine shaft and went down, that you would go past 3 layers of coal. And he knew that this kind of coal was also over in this part of England. And he finally made a map. He said, in all of England, this kind of coal is at this layer, but it's as if the whole country had been tilted. So here it's at the surface, but here it's down underneath. Okay, you might be bored with this, but let me tell you, if you were running a coal operation at the time of William Smith, and he said, I can tell you exactly how far down the coal is in this part of the country, you'd say, okay, this is worth $1 million. So they paid attention, and when they found out that he was right, of course when they found out that he was right, they stole his work and threw him in debtor's prison because he couldn't pay his debts because they had stolen his work and he couldn't sell it. Very sad story, but eventually he got out. But he was the first one to actually perceive that there were these layers that it wasn't just a question of, oh, I have coal and you have limestone. It was a question of layers all the way across, comprehensive. And then we began to understand that some of this stuff can be found worldwide. In the Paleozoic, before the Cambrian, we think there was life, there was plenty of life. But afterwards, the seas were rife. For fossilized in rocks as dark as night, we find the forms of the trilobite. You should remember when you go fishing that the grandmother hagfish swam the Ordovician. The hagfish is a particular kind of fish that it's the beginning of the vertebrate family, and it turned up in the Ordovician. The corals were still, but the sharks were hurrying through the great seas of the warm Silurian. That's the next era. And it's the era when you had fish, but without bones, just cartilaginous fish. Fishes were first bony in the Devonian. Okay, and then there's this whole period worldwide where there's just a lot of flooding. I don't know why, but flooding the marshes so we could have coal. The seas of the Carboniferous drank forests whole. And then we come to the end of the Paleozoic. Alas, alas, Dimetrodon, born in the Permian, you've come and gone. He was one of the early dinosaurs. The Palisades, more cliff than hill, stand a doleritic sill from the Triassic, if you will. Long, long ago, listen and hark, birds and dinos left their mark in the great Jurassic Park. So that's the beginning of the birds. And it's the high water of the dinosaurs. A mammal had to be courageous to walk the chalks of the old Cretaceous, for the dino giants had jaws most spacious, yet they all died out, carnivore and herbaceous. Of course, it should be herbivore, but herbaceous, it was just a word that wanted to get in there, and so I said, yeah. So Paleozoic, old times, Mesozoic, middle times, Cenozoic, recent times. To prosper the tertiary, mammals were guided because the moon blew down and the eons divided. There were mammals in the Mesozoic, but they were smaller than the dinosaurs. And they moved more quickly. Remember, if you're as big as a dinosaur, think about this, and you get cold, how long is it going to take to warm you back up? Right now, a snake will eat a rat if it's warm enough for the snake to move. But if it's cold and the snake isn't moving, the rat will eat the snake. Okay? So just think about being a dinosaur and getting cold. So after this, whatever it was that happened, when life changed, and it really was, that really was a worldwide change. There weren't any more dinosaurs. And the mammals which were already there all of a sudden took over, got big, and ran the whole world. You could have swum Everest in the Paleogene till it climbed Siberia and ceased to be marine. So that's when it happened. No new reptiles have ever been seen since the last days of the Paleocene. This is talking about the fact that evolution has specific steps that it takes. The dinosaur has not re-evolved, and all of the kinds of reptiles that we have now had evolved by the end of the Paleocene. The ultimate families of wildflowers blazed in the Eocene's golden hours. All of the flowers that we have now, we can see their families in the Eocene. The orders of mammals beheld the dawn before the Oligocene was gone. There are no new orders of mammals since that time. That part of evolution is over. Now, the Neogene critters were much like ours, more toes perhaps to tread the same flower. So you had horses, but they had several toes instead of just. Okay. The Miocene gave a horse who was short and produced the last birds, or the last bird sort. And the Pliocene gave us the primate clan, apes and monkeys, all but man. We come at length to quaternary times, to men, of God and monkeys mimes, because we're like both, really, right? Living not only by bread, but rhymes. The Pleistocene is early man. We really do not know its span. And the Holocene is the recent past. It's 10,000 years, when men began to farm at last. So these are the eons, the ages, the scenes, the zoos of the earth, the once have beens. So if you memorize that, when you start your first geology course, you'll be on top of things.